Hi, Dr.
All right, guys. So let's get started. Um, so yeah, we're not going to do a lab today. We're actually going to go fairly short. We're going to do just like an hour's worth of lecture. Um, uh, what I want to address first is exam three. At this point, we finished up uh, all the stuff we're going to do for chapters 25 and 26, which will be on exam three. So my plan is for that exam to happen on Monday. Um, how's the homework looking for that chapter? Hopefully, you guys have all started it. I can check myself, but I suspect I will be disappointed by some of you. Not naming any names, but I'm giving you a glaring look through the computer. Um, again, just to remind you that exam is going to cover chapters 23, yeah, 20, 23, 24, and then 25 and 6. So the last three homeworks. Those homeworks will also be due on Monday when the chest goes live. So you're on borrowed time if you haven't gotten started. The 24 homework is very, very short. The 25, 26 homework is very, very easy, but you still have to do it.
Dr. Fleming, for 25, where's 25.4 and 25.6?
25.4.
Yeah.
And what about 25.4 and 25.6?
I didn't see them when I was looking at the list of homeworks.
So here's a dumb question. Are you looking at it from the module section, or are you looking through the assignment list?
I think I was looking through the assignment list.
That's probably why. That's a not the best way to do that, because sometimes the order is weird. However, and I suppose this is a screenshot worthy sort of thing, but if you go in, I have things organized by module. So if you go into the modules on Canvas, you'll see all your quizzes will be lumped together. Your labs will be lumped together. We may or may not do this lab later this week. I'm not sure if we're going to do it or not yet. The readings are lumped together. And if you go into your homeworks, here's 25 and 26, and they're all there.
Okay.
So that's probably the easiest way to access them. But for some reason, if you're not seeing them in the assignments list, it could have to do with the fact that the assignments list, the order can be altered by me dragging things around, or sometimes it even just shows up in the order that the question was created. So if I deleted the old 24.6 and replaced it with a new one, the new one would show up at the bottom of the list. There may be other things interceding in between. So my guess is that's what's happening there.
Cool. All right. Thank you.
All right. You're welcome. But in terms of that exam, it's going to cover pretty much everything that we've done in those chapters. From 23, the big concepts are Faraday's law of induction. You should know how to deal with Faraday's law of induction. RL circuits got introduced in that chapter. You should know how to deal with RL circuits. AC circuits, you should know how to deal with those. There will definitely be an AC circuit question or several on this exam. From chapter 24 and 25, the big concepts are to be able to write or understand the expressions for an electromagnetic plane wave, and to be able to relate the intensity of a plane wave to things like its amplitude. For 26 and 27, you should be able to do simple optics problems. If I give you a lens or a set of lenses, you should be able to figure out where the image will form, what the magnification of the image is going to be, know the difference between virtual and real images, and be familiar with sign conventions for all those kinds of problems. So, that's what we're looking at. So we might take some time on Friday to to review stuff, but probably not that much time, since you can always go back and rewatch lectures. So there's not much point in me doing a lecture live for the purposes of review when you have that capability for yourself. Are there any questions about that exam?
Yes, I have a question about something
Huh?
in the chapter.
Okay.
So, during one of the lecture, you said that when it's on chapter 23 though.
Okay.
You said that when V is equal 0 at t equals 0, I is equal to I max sine WT minus the angle when I is lagging.
Okay. Yeah. So what was your question?
So I want to know, is it going to be the same when I is leading as well?
No. So here's what's going on with that. This whole idea of lagging and leading. So in any AC circuit, I don't want to share this screen. Stop it. In any AC circuit, what's going to happen is both the voltage across any of the circuit elements and the voltage from your power supply, and also the current, all of those things are going to vary sinusoidally. Oh, I know why I unplugged it, idiot. Let's try that again. Come on. Sorry, I unplugged my document. All right, can you guys still hear me? Okay, good.
Yeah.
Cool. When I plug in the document camera, it changes where the microphone is, so I was concerned there might be issues. All right, let's try this for like the third time. There we go. Awesome. So what's going to happen is, let's say that you're looking at the current in your circuit as a function of time, right? My current is going to look mathematically like this. Right? It's going to be some maximum times some kind of sine function. And on my drawing, that's going to be a sine wave where it's going to peak out at whatever number Imax is. It's going to go from positive Imax to negative Imax and back and forth and back and forth. All right. And what's going to happen is, if your current and your voltage are in phase, then what's going to happen is the voltage would look very similar, right? It's going to max out at the same time. It's going to cross zero at the same time. It's going to get negative at the same time. So your voltage in that case would look like V equals some V max times sine of omega t. But this only happens if your AC circuit is at the resonant frequency, right? At the resonant frequency, XL and XC cancel each other out, and your current and your voltage are in phase. They rise and fall together. But when you're off the resonant frequency, what's going to happen is one of these two curves is going to get shifted either forward or backward in time. And so they're going to hit their maximums at different moments. And when we talk about a phase shift, we're talking about how far one or the other has been shifted forwards or backwards. Now, traditionally, what we end up doing is we say, let's choose one of those two curves to be like my frame of reference. And so maybe I'm going to pick the current
as my frame of reference, right? And what's going to happen is my current, I, might start off at 0 at time 0. That means that I would still write the current the same sort of way that we did a second ago, right? The same sort of equation for the current that I'd used previously. But what's going to happen is, depending on whether my current lags or leads the voltage, my voltage curve is going to get shifted one direction or the other. So let's have the current lead the voltage. I'm sorry, what? I didn't catch that? Okay, I'm going to assume that that was a mistake. So imagine that I shift my current forward, or my voltage forward by a certain amount. So now what's going to happen is I've got the same shape curve, but what's happened is I've shifted it forward by some phase angle. Does that make sense?
Mm-hmm.
So what's going to happen is I won't write my voltage expression looking like this anymore because I have to include that phase shift. So what I would do is I would write that V equals V max sine of omega t, and depending on whether I shift it forwards or backwards, it would either be plus or minus that phase shift. So traditionally what happens is we always assume that the current starts off at 0 at time 0, so there's no phi factor in my sine expression for that. Then the voltage, if it's out of phase, will be plus or minus some phase shift. And if it's plus, that means that the voltage leads the current. If it's minus, it means the voltage lags the current. What's annoying, though, is depending on how you want to express yourself, there's another way you could do it. Think back to like when we first did coordinate systems back in chapter 2 in physics 1. Right? You could describe the position of an object in reference to some frame of reference that you're free to choose. So if, I've got two buddies standing next to a tree and I use my tree as the frame of reference, maybe person number 1 might be at position x equals 2 and the other person might be at x equals 3. But I could have chosen one of the people to be my frame of reference, in which case one of my people would be at x equals 0 and the other person would be at x equals 1. All I'm doing is redefining how I refer to those locations. And sometimes you do the same thing with AC circuits. What if instead of using the blue curve as my frame of reference and saying, aha, this is time 0, what if I just redefined what time 0 is? What if I had time 0 start right here instead of right here? Well, in that case, what's going to happen is my red curve looks like a regular sine wave. So if I'm choosing time 0 to be here instead, I don't want to have this plus or minus phi here. I would take that out and have just sine of omega t. Except now what's going to happen is my current is no longer matched up. I have to shift my current a distance phi away. So what I do is I modify this and go plus or minus phi. Does that make sense, Linda?
Yeah. Yes, it does.
Yeah. So one of your homework problems is like that. It goes out of its way to tell you to take time 0 to be when the voltage is 0 rather than when the current is 0. So a lot of the equations in your textbook are written with the sine of omega t, but no phi on your current, but then a phase shift on your voltage. But the way that problem is set up, you want to do the exact opposite. You want to leave this with no phase shift, and then phase shift this in the other direction.
Right. So when the current is in front, hold on, is that the current? Yes. When the current is shifting ahead of the voltage, is it gonna be positive?
So when you write it the normal way, if you would have, like, say, for instance, if I'm using the current as my frame of reference, I'm choosing x equals 0 or t equals 0 to be here. If I get a phase shift which is positive, that tells me that the voltage leads the current and the current lags the voltage,
Okay.
right?
All right.
So normally what would happen is a positive value for phi means that the voltage is leading, and a negative value for phi means the current is leading. However, notice that if I'm using this as my frame of reference, then what happens is my shift is in the other direction. So what I would do there is I would change the sign on phi. And the way you calculate phi is the tangent of that phase shift is XL minus XC over R. So if I was doing this the normal way, I'd get a number for phi, and then I would just take my voltage and be, if this was a positive number, I'd go omega t plus that positive number. I would add that positive number if my voltage were leading, and I would subtract if my voltage were lagging.
Okay.
If I'm doing it the other way, all I would do is switch the sign, then plug in. Does that make sense?
Mm-hmm. Yes, it does.
Yeah. It's super fiddly and confusing, but conceptually, that's the idea.
Okay.
All right, I see somebody in the peanut gallery has a question. What have we got there? What is the R of the? What is the R of the resistor? I mean, it doesn't matter. Notice the direction of my phase shift doesn't care whether what R is. It's going to matter whether this numerator part is positive or negative. But yeah, R is the resistance, and what R will do is, like, if R gets bigger, it won't make my phase shift go from positive to negative, but it could make it get bigger or smaller. So, the phase shift that I end up having depends mostly on XL and XC, and R only has a very minor role in the size of the shift, but not the direction of the shift. And if I ever get confused, the thing that I remember is I can draw my phasor diagrams. That's VL, VR, and VC. And what's going to happen is if I have a positive phi, that means I'm here. And that means that I'm closer to VL than I am to VC. So that tells me XL is bigger than XC if I have a positive phase shift. And if I have a negative phase shift, that means that VC is bigger than VL. So I'm closer to VC. All right, get another question from the peanut gallery. What's going on with that? Come on, problem. All right, Zoom, you're being a jerk. Come on, help me out here. There we go. So if there's no resistor, we just take the inverse tangent of XL minus XC? No. If there were no resistor, then what's going to happen is I'd be dividing by 0 here, right? If you divide by 0, that makes this entire thing be either positive or negative infinity. And if you take the inverse tangent of infinity, you get either pi over 2 or negative pi over 2. In other words, if there's no resistor, my phase shift is either going to be straight up, so 90 degrees if VL is bigger than VC, or negative 90 degrees if VC is bigger than VL, but it won't ever be anything in between. It's either positive 90 or negative 90, pi over 2 or negative pi over 2. So taking the resistor out takes out the sideways component of this little vector here, and it only straight up or straight down. All right, any other questions about old business before we start on doing new things? So what I want to talk about right now is, let's talk about optics, but let's remember that electromagnetic waves are waves, and that means that light behaves in certain ways that is only understandable if you think about it in terms of waves. And I want to do kind of a thought experiment regarding the behavior of light. And then we're gonna run a simulation that actually performs that experiment to see how it plays out. But here's the scenario, right? Here's one of these classic problems that we've dealt with in physics. So let's imagine that I've got source of light, like a light bulb. And that light bulb is giving off electromagnetic waves in all directions. And then let's have some of these light rays. I'm going to pay attention to the ones that are traveling sideways, and I'm going to be sufficiently far away from the light source that the kind of spread of the light rays is negligible, and I'm so far away that the light rays are basically coming in parallel. So I've got a bunch of parallel light rays, and then what I'm going to do is I'm going to have those be incident on like a wall, except in that wall, I'm going to make two little tiny slits. Here's a tiny slit. Here's a tiny slit. Now what's going to happen is these slits are going to be so small that on the other side of that wall, it's going to be like having two little pinholes. I'm going to have two little spots of light. And those two little spots of light are going to cross a room, and they're going to get projected on the far wall. So here's a dark room, two little pinhole specks where light can shine through. And what I want to imagine is, what is the image that I'm going to see on the far wall going to look like? So if you had to predict what you would see if you had two little pinhole specks projecting on the wall, what would it look like on the other side?
Like spread out, I guess, maybe.
So when you say spread out, can you be more descriptive, perhaps?
Like, I think like that it'll like the light will try to go through those two specks, but like not all of it will fit, basically. So,
Well, yeah, I mean, a lot of the light's is gonna hit the wall and not get through, but I am gonna have light come through these little specks, and the light's gonna shine in every
Would
direction.
it cross? Like it'll go through and then cross?
So if I'm looking at like what the light looks like on that far wall, what would I expect to see? Would I see a spot?
no,
Some
you
straight line.
a straight line.
Like
Wouldn't it be fanned out?
Yeah,
Okay.
that's what I was saying, like fanned out. Yeah.
So what's going to happen is, make sure I'm visualizing this right. So I'm going to have light come kind of do-do-do, do-do-do, do-do-do.
Yeah.
Mm-hmm.
right.
And then from the other hole, I'm going to have do-do-do, do-do-do, do-do-do. So what's it going to look like when the light from those two little holes lights up the other screen?
Well, if they're like crossing, won't the screen just be bright?
Okay. But will it be uniformly bright? Will it be equally bright everywhere?
No.
No.
Okay. Where would I expect it to be brightest?
The middle.
Like smack dab in the middle?
Like where the lines are
Like
crossing.
across from this speck it'll be bright, across from this speck it'll be bright.
Yeah, like that.
Right.
Okay. So what you're telling me is that if I have two little specks here, then what I ought to see on the far screen, if this is my screen, I'll see a little bright dot across from one speck and another bright dot across from the other speck.
Wouldn't it be just one in the middle of both of them? Like,
I don't know. Convince me. Because if you think about it, the brightness that you see on the screen is going to depend on how many rays are going to hit that spot, right? And what's going to happen is there's going to be a whole bunch of rays that go right through and hit the spot here. You'd expect there to be a whole lot of rays that go right through and hit the spot right here. So I expect to have a lot of brightness there and a lot of brightness there. And then not as many rays are going to go this way, but there's going to be some from this slit that hit here, making this brighter. There'll be some that go this way, hitting there, making this brighter. And so what you might expect is a whole bunch of brightness here and a whole bunch of brightness here, and then for it to get dimmer, 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 dimmer in either direction. And prior to about 1900 or late 1800s, that's what we thought should happen in this experiment. We thought that if you have two little pinholes and you shine light through the pinholes, that on the opposite side of the screen, what you should get is two spots of light, one for each pinhole. Except when you do this experiment, that isn't what you see. In the real world, you see something different. And in order to make sense of why you don't see on the screen the same thing that you expect to see, we have to start thinking about light not as little rays that travel in straight lines like we did in the previous chapter, but instead as waves that have properties of waves. And one way to think about that is that the light in question is doing two things. So here's my two little pinholes. And here are parallel wave fronts heading towards my pinholes. And the first thing I have to understand is that the fanning out thing that you guys imagined, that's totally real. That totally happens. But the reason it happens is because of a process called diffraction. Right? And diffraction is something that waves do. It happens when waves pass through very narrow openings. And it happens because as the wave interacts with the edges of the little hole, the wave at the edges slows down a little bit for the same reason that it slows down when it goes from one medium to the other. But here in the middle of the hole, the wave doesn't slow down much at all. So the middle of the wave, it travels a little faster than the edges of the wave. And when it comes out the other side, it comes out sort of curved. I've got a simulation that kind of does the same thing, but it's not limited by my craptastic artistic skills. Craptastic is totally a word, by the way.
It is a word.
So here's what we've got. So here's my little wave generator, and it's going to generate a series of electromagnetic plane waves. Those are things that have a formula like, E naught equals sine kx plus or minus omega t, that sort of thing. And visually, the way I would see that is, if I turn this thing on, the tops of the waves are the bright blue. The bottoms of the wave are the dark black. And so what you're seeing is the wave kind of travel from left to right away from my wave generator. So far, so good? But then what's going to happen is I'm going to add a barrier with a hole in it. Let's just do one hole for the time being. And what's going to happen is up here, here's the part of the wave that just hits the wall and gets absorbed. It doesn't go through at all. But right here, you can see diffraction occurring. The middle part of this wave keeps traveling at the same speed the whole way. But the edges of the wave slow down a little bit, and that causes them to create this sort of bendy effect. And as a consequence, I get rounded wave fronts that are much more difficult to mathematically model on the other side. But that's what's happening when these rays of light go through these narrow slits, is they create waves that emanate in this sort of circular pattern. And let me pause this for a second. If you were to think about light in terms of rays, the way we did in chapter 26 for a second, what those rays would look like is the rays of light would always be perpendicular to the wave fronts. So for instance, here on this side, my rays of light are traveling perpendicular to those wave fronts. So they're all traveling to the right. But here on the other side, what's happening is the perpendicular to those wave fronts kind of spreads. Does that make sense? So what I'm seeing is the light sort of branching out and spreading the exact same way you guys were expecting them to. So far, you haven't really seen anything that is super surprising. We've just sort of seen the underlying reason for why the thing you expect to happen is happening. why the light goes through the pinhole, and instead of going in a straight line, it spreads out. That's the process of diffraction. And diffraction is going to occur anytime you send a wave through some sort of narrow opening. In fact, if you take your fingers, and I love this, if you take your fingers and you bring them right up close to your eyes, and you press your fingers super, super close to each other, what you'll start to see is there'll be this moment where it looks like your fingers are starting to touch before they actually touch. And the reason you see that happen is because the light is going through that gap and it's bending out, and the intensity of the light that goes through the middle is sufficiently dim that you can't make it out anymore. So it kind of looks like your two fingers meld together a split second before they actually make contact. Kind of cool. So what I want to do is I want to add another slit, and what's going to happen is I'm going to get waves on the other side that look like this, but they're going to start interacting with each other. So let's do this. Let's add a second slit, and let's move it over here. And what's going to occur, I'll have to pause, that's why, is the light is going to diffract through each of the two slits. But look what's happening on the other side. What the heck am I seeing?
A bright spot that you can see in the middle where they meet.
Sort of, yeah. Because you can see that, like, right here in the middle, like, this looks very, very similar to my original wave on the other side. So right here, there's lots of light happening. There's a wave that's occurring right in this region here. But look at this region right here. What's happening right here is I got this kind of plain gray band where it's kind of blurry and blah, right? Here I see another one, a gray band where it's blurry and blah. That looks not unlike, well, no wave at all. So what's happening, and we talked about this a little bit last semester, is that when two waves overlap, they undergo something called interference. And interference is super easy to wrap your around on a conceptual level, because all that happens when two waves overlap is you just add up their amplitudes. So your amplitude of the total wave is just the sum of the amplitudes of the individual waves. And the way I usually demonstrate that during Physics 1 is with this bad boy. So what I'm going to do is I'm going to create little wave pulses, and I'm going to do it on a fixed end here. And let's take the damping off. So if I just hit this button, I'm going to create like a little wave pulse that goes back and forth, and every time it hits the end of the string, it bounces back and reflects back the way it came. And what I'm going to do, let's actually, I don't like this one as much. Let's fixed end, no damping. Let's make my wave width a little bit shallower. Yeah, it's a little better. So what's going to happen is I have this little triangular waveform that is bouncing back and forth. And I'm going to create a second waveform. And as they pass back and forth, they're going to pass through each other. And there's going to be moments when the two waves are overlapping. And I want to pay attention to what's happening when they overlap. And let's... There we go. That's a little better. So what's going to happen is you'll notice as these things strike the edge here, sometimes, depending on which end of the string they're hitting, the amplitude of the wave will reverse. When it hits the end of the string with the loose end, you'll notice the amplitude doesn't reverse. But when it hits the one with the fixed end, it does reverse. That'll be important for understanding some stuff later. But don't worry about that right now. what I want you to pay attention to right now is what happens when those two waves are overlapping. And I'm going to put this in slow motion so that it's easier to make out. So what you're going to see is there are two conditions that we sometimes end up with. Right? There are some conditions, like what we're about to see in a second, where both of my waves have amplitudes in the same direction. Here, both of my amplitudes are negative. And as I step this forward, as they start to overlap, it changes the shape of the wave. So here they are, I went too far, basically completely overlapping. And the thing you'll notice is that this wave is much taller than the individual waves. Right? We call that procedure constructive interference. And what's happening, if I were to measure it, I would find that the height of the two things combined is exactly twice the height that I had of them individually. I literally just add 1 plus 1 to get 2. However, if I let this swing forward a little bit, now you'll notice I have a situation where I'm about to collide a wave with a positive amplitude to a wave with a negative amplitude. And with this idea of adding amplitudes, if I have positive 1 plus negative 1, it should add up to 0. And lo and behold, what's going to happen is at the moment the two waves completely overlap, there's no wave at all. The positive wave and the negative wave have exactly canceled each other out, creating a string with no disturbance. Now, each of the waves are continuing to move, and if I let it pass forward, they're going to pass right through each other and appear again, and now I've got constructive interference. Then I wait some more, and I'm going to have a split second of destructive interference. And so constructive and destructive interference are a concept that we talked about last semester. And what we're seeing it right now with light is constructive and destructive interference. So what's happening is the wave that's passing through that top slit is interfering with the wave that passes through that bottom slit. And there are regions where you're getting constructive interference, because the top of the wave from the top slit and the top of the wave from the bottom slit, they both overlap at the same time, creating an extra big wave at that location. And there's other locations where every time the peak of one wave arrives, at that exact same moment, the trough of the other wave arrives, and they cancel each other out. That is what's happening consistently along this little band here. Now, what's that going to look like when I project it on a screen on the other side? How am I going to see this if I'm looking at it in real life? Well, to make that work, let's minimize that for a second. What I'd like to do, if I can get the controls to work, yeah, I want to be able to see what's happening on a screen. That's not what I want. This is a new version of the one that I had previously. Sort of annoying. Where's the button for the screen? Not what I want. All right, let's swap versions then, because this is not showing you the thing that I want to show you. Got really excited when I saw there was an HTML5 version of this sim, because the one we used last semester was not HTML5. So let's go back to the old version, which is probably me. Oh God, did they deprecate it? Is it gone? Very much sadness. Surely it's not in this one. So there's a screen on this one. I want the screen on mine. You are cramping my style, simulation. All right, I'll do it this way. Does this one at least have a screen? No, none of them have a screen. All right, doggone it. All right, so what's going to happen, this is definitely cramping my style, is we're going to get so we're going to have to just do this the hard way. I've got a little graph that will measure the size of my electromagnetic wave at different locations. And if I go right here, halfway between the two slits on the other side, and I measure right there, what you can see is that the intensity of my wave is pretty large. I have a pretty large amplitude. You'll notice that the amplitude here so the amplitude here and the amplitude here are different, but I've got a very noticeable electromagnetic wave at this spot. So if I was looking at this portion of the far wall, I would see something bright. However, if I move up here, you'll notice, if I get it just right, there's a spot where I hardly get any wave at all. So that location would be exceptionally dark. Now, what you can't see is that if I keep moving this further, you'll notice the wave starts to get brighter again. I'm getting more and more light the further up I go. And it turns out that if I modify, let's say, the separation of my two slits, you'll notice that this feature becomes a bit more pronounced. You can see this region right here where I'm getting destructive interference. You can also see the beginnings of another region out here where I'm getting destructive interference. If I increase this even more, you'll notice that the separation between this region of destructive interference and this region of destructive interference is getting smaller. If I crank my frequency up and make the frequency of my light get even larger, you can see it even more apparently, right? You can see that here's a region of lots of destructive interference. Here's constructive. Here's more destructive. Here's more constructive. Here's more destructive. So I'm getting a pattern of alternating levels of brightness and darkness depending on where I look on the screen. So rather than see a bright dot and a bright dot across from each of the two slits, I'm seeing something way more complicated and interesting. So apparently I'm going to have to draw this for you, which I'm not happy about. So what's going to happen, if you were to look Here's the two slits. And here's the far wall. What you expect to see is a bright spot here and a bright spot here. But what you in fact actually see is that you get one spot where if I'm looking at the intensity, right here in the middle, the intensity, the brightness of my light is extremely large. Then I have a dim place where there's hardly any intensity at all. Then I have another bright spot, then another bright spot. And if I keep going, I'll get a dim spot, another bright spot, a dim spot, another bright spot. So what I'm going to see on the far wall are patterns of bright and dim, bright and dim, bright and dim. And this is what we call an interference pattern. And it only occurs because of the wave nature of light. Now, in order to understand why the interference pattern looks the way that it does, and why, more importantly, I should care about this, I need to think about why it's happening. Why are certain places always getting destructive interference and other places always getting constructive interference? The reason this works out that way is because if you think about what's happening, I've got waves leaving each of these two pinholes, if you will. And if I were to look at those waves, they would look something like this. So here's a wave, here's a wave, here's a wave, here's a wave. And over here, here's a wave, here's a wave, here's a wave, here's a wave, here's a wave. And what's going to happen is, at any given moment, I'm going to have wave peaks leave these two slits at the same time. And these two wave peaks are going to travel across the room, taking a certain amount of time to get across the room. And I'm going to get constructive interference if those two wave peaks arrive simultaneously, because the peak from one wave and the peak of the other wave arrive at the same time. They add together, making it extra bright. And right here in the middle, I can be guaranteed that that's going to happen, because each of these two waves has to travel a certain distance. And from symmetry, those two paths are the same distance long, and therefore, since the light is traveling at the same speed, it will arrive at the same time. Does that make sense? Because this distance and this distance are the same. Here in the middle, I'll get constructive interference, and I'll get a bright spot on the screen. But what's going to happen is, if I look a little bit above that on the screen, I'm a little bit further from this slit than I am from this slit. So if these two wave peaks leave the slits at the same moment, this guy here is going to arrive first, and this guy here is going to arrive a smidge later. And if I pick that spot just right, then what can end up happening is this peak will arrive, and then when this trough arrives at that same spot, that's going to be the same moment that this peak arrives. So this peak cancels out that trough, and I get a dim spot. So I'm getting destructive interference when this path is a smidge longer than that path. However, if I keep going up the screen, this path is even longer compared to the other path. And what's going to happen is, these two wave peaks that leave simultaneously, they won't arrive at the same time. However, the bottom wave is going to be delayed, and if it's delayed at just the right amount, what could occur is that this guy will hit the screen and be gone. This guy will hit the screen and be gone. This peak here, the second peak, will hit there at the same moment the first peak finally makes it to the screen. So if I go further up, what's happening is this peak, the second peak in line up here, interferes with the first peak down here. If I keep going up even further, there's a spot where the third peak from the top screen that's closer will arrive at the same time as the first peak from this one, and so on and so forth. So I'm going to have several locations where one peak or the other will arrive simultaneously, and I'll get constructive interference. And all these dark places in between, that's where the peak of one and the trough of the other always arrive at the same time, and so they always cancel out. And so it will appear on the screen like there is no light falling on it at all. Now, to quantify this, because we love to quantify stuff in physics, what I care about is how much different this path is from that path. So what I'm going to do is I'm going to call the difference in this length and this length delta L. So delta L is going to be how much longer the bottom path is compared to the first path. And what's going to occur is if the difference in path length is exactly the same as the wavelength of my light, then what's going to happen is this peak will arrive at the same time as one of the other peaks. So if delta L is going to equal the wavelength of my light times any integer I imagine, so m could be any integer. It could be 0, 1, 2, 3. So if m is 0, that means that delta L is 0. That's the spot here in the middle. If I pick m to be 1, that means that delta L, the extra distance for the bottom peak, is exactly one wavelength, and this peak and that peak interfere. If I pick m equals 2, I'm talking about this place up here, where this peak will interfere, or sorry, where this peak will interfere with this peak, and at m equals 3, I'm exactly 3 wavelengths away, so this peak will interfere with this peak. Does that make sense?
Yeah.
So if this condition is met, I will have constructive interference. And therefore, I will see a bright spot.
What is delta L again?
Delta L is how much further the one slit has to travel compared to the other slit. That's the concept. Is that if they have to travel the same distance, I'm going to get constructive interference. Because if they're both traveling the same distance, that means that delta L, this L and this L are the same, so delta L is 0, and that means that they'll both arrive at the same time and they'll constructively interfere. But if the difference is exactly one wavelength, or 2 wavelengths, or 3 wavelengths, I'll still get constructive interference because this first wave will interfere with the second, or the third, or the fourth guy in line from the slit that is further away. So that's my condition for constructive interference. Destructive interference is going to happen like right here. And it makes sense that if the delta L between here and here is 1 wavelength, and this is 2 wavelengths, this has to be halfway in between there. So mathematically, the way I would write that is that I'm going to get destructive interference if the difference in path length is not a wavelength, but it's off by half a wavelength. So it could be m plus 1/2 lambda. So if m is 0, it'd be half a wavelength different. If m is 1, it'd be 1.5 wavelengths different. If m is 2, it'd be 2.5 wavelengths. But it's always going to be something and a half. If it's that many wavelengths off, I will get destructive interference. So those are my conditions for when constructive interference and when destructive interference will occur. And it's going to be all based on how far the 2 rays of light have to travel in order to hit that screen. So far, so good?
Yes.
So now I'd like to figure out what the heck is delta L. How can I quantify how much different the path length is depending on where I look on the screen? And the way we're going to do this, I'm going to zoom in a little bit. Let me redraw, but zoomed in. So here is the top slit. Here is the bottom slit. And what's going to happen is the light from this one is going to go off like this somewhere. The light from this one is going to go off like this somewhere. And usually when we do these experiments, we assume that the room is sufficiently long that the angle between these two things is very, very close to zero. In other words, they're almost, but not completely parallel. And we're going to make our lives easy by pretending that they are basically parallel, because it's going to make it easier to do the math. So these two light rays are going off to hit the screen way, way over there. And what's going to happen is, if I were to draw a line straight from here, perpendicular down, from here on out, this distance and this distance would be exactly the same. So none of this stuff matters. All that matters is this little section right here that the bottom slit has to travel extra. This right here is that delta L. Does that make sense? And what's going to happen is that's perpendicular, and I've got a little triangle going on right here, which means I can use right triangle trig. So if I take the distance from one slit to the other slit, we're going to call that D. So D is how far apart the two slits are. And I'm looking at this angle right here. Then delta L is the opposite side of that little triangle. So I can say that delta L is D times the sine of whatever that angle is. And that's going to be true regardless. So now, if I take that, I go back to my expressions previously, replace delta L with D sine theta. And rewrite my two conditions. This is constructive, and this is destructive. Because all I'm doing is replacing delta L in these expressions with that. And the cool part is that, back to my big picture here, if I go and measure the angle, crap, let's try that again. So here's my screen. If I go straight across the way, and I measure what angle I have to go from here, in other words, if I go up to there, and I call this theta, the further up the screen I go, the bigger theta gets, and this angle here just happens to be geometrically the same as that angle here. So in a way, what I've got is I know that if I'm looking straight ahead at an angle of 0, I'm going to get a bright spot. But then if I go a certain number of degrees up the screen, I'm going to get another bright spot. And it's going to happen when I go a certain number of degrees up the screen, given by this. So what we're instead doing is we're measuring the angle up or down the screen that we have to go to see these bright or dark spots.
So from a bright spot to another, is it gonna be like the same angle over and over?
Well, you'll notice that the angles that we're going to get are going to depend on a couple of things, right? The angles we're going to get are going to depend on how far apart my slits are. They're also going to depend on what wavelength my light has. So different wavelengths are going to have the bright spots separated by different angles. Does that make sense?
Yes.
So that's what we're seeing here. We're watching those bright spots and dark spots either get further apart or closer together. What will occur is we'll be able to do all kinds of fun stuff. Let's go back to my sim. So inexplicably, it doesn't show me the thing that I do want, but it does show some of the applications. So, have you guys done any like X-ray diffraction in perhaps like PChem maybe, or analytical?
No.
Any kind of crystallography at all?
No.
Usually you do. So here's what we're going to do. Let's say I've got a little piece of some kind of solid, like a piece of crystal. Now, what is that crystal made out of? Atoms. And they're atoms that are going to be spaced with some periodicity. In other words, each of these little dots, imagine that that's an atom, right? And what I'm going to do is I'm going to shine my light through this crystal. And if you think about it, these gaps between atoms, they're kind of sort of like the holes in my screen. In other words, this is like having a screen with not just 2 slits, but with a whole bunch of slits. And what's going to happen is my light is going to pass through those slits. Now, the mathematics for what's going to happen here with lots of slits is exactly the same as the math you'll have with only 2 slits. And the only real difference you're going to see is how sharp the cutoffs are between the bright spots and the dark spots. In a 2-slit experiment, what's going to happen is you'll have one really big bright spot in the middle, but it's going to be kind of blurred and spread out. And then it'll gradually shift to another bright spot, then gradually shift to another bright spot. But with lots and lots of slits, what's going to happen is the places where you get full-on constructive interference tend to be very, very tightly defined. So you'll have a single very narrow bright spot, then a single very narrow bright spot, and all the bright spots won't be as spread out. They'll be much more well-defined. So if I shine my laser through this crystal and project it on a screen, this is what I'm going to see. So what you're seeing are 2 things, one on top of the other. One of them is called a diffraction pattern, which we haven't talked about yet. But the other is this interference pattern. And what I'd like you to pay attention to is, don't pay attention to the ring-like structure. Pay attention to what's happening if you go sort of horizontally. You'll see that, like right here in the middle, it's like super, super bright. But then what's going to happen is it gets a little dimmer, then brighter, then dimmer, then brighter, then dimmer, then brighter. And as you move out to larger and smaller angles on either side, you see this pattern of bright in the middle, then it gets dim, and then bright, then dim, then bright. That's what you're seeing. And the cool thing is that if I change the wavelength, you'll see how the spaces are getting further apart? If I increase the wavelength, the spaces are getting closer together. So the distance between bright spots and dark spots gives me information. Because remember, the spacing between those spots depends on 2 things, the wavelength of my light, but also it depends on the spacing of my atoms. Watch what happens when I make my atoms get further apart. Right? So you can see the pattern that I get depends on the tightness of my lattice. When my lattice gets super, super tightly spaced, it tends to spread my maxima and minima apart. My central bright spot is further apart from the first order bright spots. And so what we often will do is we'll use this sort of interference pattern to make inferences and figure out what the structure of my crystal is. I can determine how far apart my atoms are if I know the wavelength of my laser and I measure how far apart my different bright spots are. Super cool. Well, that's cool. I should have done that to begin with. So now I have like super tiny spots. By making my spots super tiny, it's like making my slits much, much wider. And then if I make them super big and fat, it makes them much, much narrower. So, pretty cool. Now, the reason this is not ideal, the simulation I used last semester allowed me to show the two-slit interference pattern without showing it on top of the diffraction pattern. And diffraction patterns are making this a little bit harder to wrap your head around. But it turns out that even if I only have a single slit, I still end up with some kind of weird pattern. So let's go back to a singular dot. This is, I'm shining my laser through a little tiny dot in a screen. And this is my little tiny white dot. Now, what's going to happen is this one little white dot will cause interference with itself. And you're like, what the heck are you talking about, Tom? Why would I have interference with myself? To understand where that comes from, the way we kind of model this is I'm going to zoom in. Here is my barrier, and here is the hole inside my barrier. And what's going to happen is, if I take a single spot, I can imagine that the light coming out the other side, I can model it like a whole bunch of little tiny point sources. And what's going to happen is, if I treat each of these little tiny places where the wave is as little tiny point sources of light, those little point sources can interfere with each other. And the ones here at the edges are going a little slower than the ones here in the middle. And that's giving rise to these things having a phase difference. And so you end up with this diffraction pattern even from a single spot of light. So what you were seeing in the previous example was the pattern for one slit being superimposed on the pattern for two slits. And that's why you got what amounted to this, where you can see that here is my central bright spot, and then here are my fringes where I'm starting to get interference. Now compare that to what I'm seeing when I have this. Right, you can see that as I modulate this, you can see that I have the same sort of ring structure on top of the two slit interference. So the little tiny bright, dark patterns, that's the two slit interference pattern. It's superimposed on the broader pattern. The diffraction pattern means I'm always going to have a dark spot here anyway, even with just one spot. So because this is always dark for one spot, it continues to be dark with lots of spots. So it's just a combination of both of those things. So what this is typically important to know for is in interferometry or in spectroscopy, or not spectroscopy, crystallography, what we're often looking at is how do those peaks depend on the spacing of some periodic lattice? How can I infer information about the size of my specks based on the pattern that I see on the far wall? And the typical way that we'll do that is by measuring the distance, either in terms of angle or in terms of linear spacing, between my various peaks. So, some nomenclature that you should probably know. So when we're figuring out what peaks we've got, we often refer to them by their order. So for instance, when I choose M to equal 0, and I find where I have constructive interference, that would be my 0 order bright spot. Right. So on my pattern, that's going to be, here's my bright spot in the middle, then brighter, brighter, brighter. brighter. So this would be my 0 order. This would be my first order, second order, third order. And each of these corresponds to m equals 1, m equals 2, m equals 3. Notice you have symmetry, so this is also 1, 2, 3. So when we talk about dark spots, we'll do the same thing. I've got my 0 order, and then first order, second order, third order. And what we could say do is, let's imagine that I've got a 2-slit experiment, and I want to know, like, the difference in angle. So let's say that I've got 2 slits, and when I shine a red laser whose wavelength is, let's say, 650 nanometers, I get a first order bright spot at, let's say, 5 degrees. What is my slit spacing? So when I say that, what does that mean? It means that the pattern that I'm seeing on the far wall right? Here is my 0 order spot. Here's my first order spot. And apparently my first order bright spot is at 5 degrees. So the angle right here is 5 degrees. I'm looking for my slit spacing. Well, since it's a bright spot, that means that I'm getting constructive interference. So that means that d sine of theta has to equal m times lambda to get constructive interference. And because I'm looking at the first order bright spot, I'm not looking here, I'm looking here, m has to equal 1. So now I'm looking for lambda. Lambda was given to be 650 nanometers. So all I've got to do is solve for d. So in this case, d is going to equal m lambda divided by the sine of that angle. And so I can now figure out how far apart my 2 slits are based on the interference pattern that I see. Does that make sense?
So you said that m equals 1, why?
So m is the order of your bright spot. And so when I said the first order bright spot, what I meant was, you know, the 0 order is the big bright place in the middle. It's going to be the next bright place over. So this would be m equals 1, m equals 2, m equals 3. So m just tells you how far from the peaks you are.
Okay.
Does that make sense?
Yeah.
And in this problem, I got, because they said it was the first order bright spot, that means they're talking about this being 5 degrees, not, say, this being 5 degrees.
Right.
That's the idea.
So 2 questions.
Huh?
So for the 650, do you want that like to be it as that, or do you want it to be like 6.5 times 10 to the negative 9 or something like that?
It's a good question. So when it comes to units, the most important thing about units is to make sure that you don't mix and match different units. So here's what's going to happen. Let's look at the units in this expression, right? D has units of length. Lambda has units of length. So what's important is that this unit and this unit be the same. Now m, it's just a number. It doesn't even have units. And the sine of theta, that's a dimensionless number as well. So for this, if I was super lazy, I wouldn't even convert these units. I would leave it in nanometers, but when I did and I solved for d, I would be getting d in nanometers.
So would you convert the answer then, or?
Well, it depends. I mean, is it okay to answer in nanometers, or do I need it to have in some other units? But in this particular case, for this particular value, I'd be picking m as 1. I'm just going to leave that as 650 nanometers.
Okay.
And then I divide by the sine of 5. And what that tells me is if I take 650 and divide it by the sine of 5, I get 7,457
Okay.
nanometers. Now, maybe I don't want my answer in nanometers. Maybe I want my answer in meters. How many meters is that?
That'll be times 10 to the 9th.
Incorrect. 10 to the negative 9th.
Oh, yeah, 10 to the negative 9.
Yeah. So if I divide that, I multiply that times 10 to the 9th, and just convert that into, I can say that's like 7.45 micrometers is what it works out to be or 7.45 micrometers, or 7.45 times 10 to the negative 6 meters.
Mm-hmm.
So there you go.
I was just second. Oh, and then also, will M always be given to us? Like,
No, not at all. Sometimes you have to use some common sense. What if I change the question? What if I say, hey, I've got a diffraction grating where I know the slit separation is 5 micrometers. Does that make sense?
yeah.
I shine a laser on those slits, and what I find is that the width of the central bright spot is 10 centimeters when I project it on a wall 3 meters away. What's the wavelength of my laser? All right, so notice I didn't tell you anything about M in this problem. I told you how wide the central bright spot was, and I'm going to have to use some common sense to figure out what to do with M. So let's think about that for a second. I know that when I do this experiment, there's 2 things happening. Let's draw kind of a top view first. Here's a slit, here's a slit. This right here is D, and they tell me that D is 5 micrometers, so a D is no, right? But then I'm going to project that on a wall, and this distance here is 3 meters. And what's going to happen is I'm going to have a bright spot in the middle, then a dark spot, then a bright spot, then a dark spot, then a bright spot. So I'm getting bright spots on the wall, and what I know is that the width let me draw it this way. The width of that central bright spot is 10 centimeters. Now, if I look at like the intensity of my pattern is like central bright spot, first dark fringe, first order bright spot, second dark fringe, first order bright spot. So I'm seeing a pattern of intensity that looks like this.
Mm-hmm.
And what I know is that from here to here is 10 centimeters. That's what the problem just told me. So part of what's tripping me up on this problem is that it was phrased in such a way that A, they don't tell me anything about the M's, and B, they gave me distances And yet, all of my interference equations have angles in them. Yeah. You know, here is my, oh, it's on the back of this one. My interference equations have angles. Like, what the heck am I going to do with this angle? I need to have distances. So there's two things I have to think about. One, I can think about this way. Already got a clean sheets to write on, darn it. There we go. So if this is my two slits, and here's the line between them, and here's my screen, and I measure my angles like so, right? This distance right here, I'm going to call L, and in this problem, L equals 3 meters. How far is it from here to here if I'm looking at the width of my central bright spot?
10.
Not quite, because it's 10 from the very, very center to here. Or sorry, it's 10 from here to here, so it's 5 from here to here. So if this is where it gets dark, that's the edge of my bright spot is where it first starts to get dark. I have this distance right here is 5 centimeters. Does that make sense? Everywhere between here and here, everywhere in this region, it's bright. Does that make sense?
Yeah.
So when you think about the problem that way, the way I can solve it is I'm not going to worry about the bright spots at all, because the boundary of my central bright spots is going to happen where the dark spots start. I want to know where the dark spots are. So on this picture, what I really want to know is that it's 10 centimeters from this dark spot to that dark spot.
Mm-hmm.
So what is M? What is the M of this dark spot?
Is it 5?
Would it be half?
Nope.
It'd be
So
half?
go back to your equations. You're going to get destructive interference
Yeah.
at any angle where m plus a half equals d sine theta. The first one is going to happen when m equals what?
0.
0. So what's going to happen is I'm going to set m equal to 0 because at these locations, I'm going to be off by exactly half a wavelength. Over here is when I'm off by 1.5 wavelengths. This is the m equals 1, but the place I care about is m equals 0.
Okay.
Does that make sense?
Mm-hmm.
So that solves my problem of not knowing what to do with m. I want m to be 0. Now what I need to figure out is how can I relate this sine of theta thing to my distance? Let's go back to this picture. Oh, wait a second. Sine of theta is opposite over hypotenuse, right?
Mm-hmm.
So I can say the sine of theta is going to equal this right here. I'm going to call this y. So it's going to equal y divided by, I'll call it question mark. And that's this diagonal annoying distance over here. Far so good?
Yeah.
Now, here's where we're going to be super, super lazy. It turns out that for this kind of experiment, notice how the room itself is like 3 meters wide. And this is only 5 centimeters. So this picture is not to scale by even the slightest amount, right? When I look at this picture, this hypotenuse is clearly a little bit longer than 3 meters. But because this side of the triangle really is super, super, super tiny, this side of the triangle is so close to this side of the triangle that they might as well be the same. So provided that L is much, much bigger than Y, then what I can do is I can have the question mark be approximately the same as L. We're cheating, basically, to make the math easier. So now I can say that y over L is the sine of theta and I can then replace the sine of theta. Oh, what did I do that for? I'm going to replace the sine of theta with y over L. So I can go back over here and say, ha ha ha, if y is 5 centimeters and L is 3, then the sine of theta is going to be 5 centimeters, or 0.05, divided by 3. And now I can find theta. Does that make sense?
Yes.
So now, when I go back and do the entire problem, I'm using destructive interference, and I'm saying that d times y over L, because I'm replacing the sine of theta with that, equals m, but m is 0, plus a half times lambda. And I'm solving for lambda, so 2 dy over L is lambda. And I can now figure out the wavelength of my thing. So 2 times 6 times 10 to the minus 6 times 0.05 divided by 3. So lambda works out to be about 5 times 10 to the minus 7th meters, which is about 500 nanometers. Which means I've got like a green laser or something. Maybe a yellow laser.
Hold on. 2 dy. Okay.
So there are times when what's going to happen is you don't want to have your equation written in terms of sine of theta. You want to think about it in terms of distance. And so you should be able to translate those things pretty straightforwardly. But you can always replace, you can always say that y is equal to L sine theta and make that replacement.
L sine theta.
Provided that L is much, much bigger than Y.
Okay.
So that's what this is all about. It's about looking at the interference that you get and making measurements accordingly. Real quick, anybody here not have access to a microwave oven?
Me.
Okay.
What is that?
What?
I'm a little lost.
There's an experiment that I've seen done before. I've never done it in class, where you measure the speed of light by using your microwave oven and utilizing interference patterns. But if you have a microwave accessible, it might be a thing I make you do.
Have a regular microwave? I don't know what
A
this is.
regular microwave,
Microwave.
yeah. Or,
Like a microwave oven, the kind you put your food in and it gets warm.
okay, there's the oven, there's a microwave.
No, a microwave. It's called a microwave oven. It's a microwave, not the you know. Usually you have little buttons and it glows for a while and then it comes out hot.
Yeah. That's
Oh,
a
a microwave is a regular microwave.
Yeah.
Yes, it is called a microwave oven.
I
Oh,
never
yeah. So never mind, I got a microwave.
always microwave.
Yeah.
So what do you do with the experiment?
Well, what you do is you line it up with something that will leave marks. I've seen it done where you take like marshmallows and you put them on a plate and you line marshmallows all over the bottom of your microwave. You turn it on for several minutes and you watch for the places where the marshmallows burn. And what you'll see is a pattern of burn, no burn, burn, no burn, burn, no burn. I've also seen people do it where they take like little Hershey Mars squares, they line it up all over the bottom, turn it on for maybe 30 seconds or so, and you look for the place where the chocolate melts. And again, you'll see a pattern of burn, no burn, or melt, no melt. And if you're showing the spacing, you're going to be able to figure out the wavelength of your microwave. But anyway, I don't know. It's a thought that I've had. I've never done the experiment before because I've never had a microwave in the lab. But I don't know. I'll think about it. In the meantime, that's all I've got for you, so go away.
Dr. Fleming, I got a quick question.
Yes, sir.
The question is actually not pertinent to this lecture. What do you think about 5G? You know, there's a lot of negative, narratives about 5G.
Are you talking about, like, I've heard people complain about possible health hazards or
Yes.
or environmental impacts.
Oh, God.
And I'm saying this based solely on very, very limited knowledge. I haven't looked into it at all. But my guess is that those people are full of it. When it comes to, like, electromagnetic radiation, a lot of your health hazards are going to come from electromagnetic radiation that has an energy that exceeds the ionization energy of, say, your DNA. At which point, there even is nowhere close to that. So my knee-jerk response is I'm not concerned, but I'd have to look into it. I'm not exactly certain what the frequency band range is, but I don't think it's anywhere high enough for us to care. Yeah.
Okay.
So, yeah, I suspect that those criticisms are largely alarmist and uninformed. But I'm saying that having not done much specific research, so I don't want to say that too strongly because I can't say I know for sure.
I see. All right.
Yeah. All right. Any other questions?
When is all the homework due again?
So it's going to happen when the test goes live, which will probably be 3 o'clock on Monday.
Okay. And like, if we have some questions about the homework,
if you've got questions about the homework, I'm available. If you send me an email saying, "Hey, I want to meet with you," I'll send you a Zoom link. We can talk stuff through. That's what my office hours are for. So take a look at my office hours on Canvas. That's when I'm sitting by my computer at all times, just waiting for someone to come talk to me. If you want to meet with me outside of those hours, I'm perfectly willing to do so, but give me a bit more advance notice because, sometimes I, hang out with my wife and sometimes I watch TV and sometimes I'm just sleeping. So
okay.
I don't want to, get random calls at random times, but I'm also pretty flexible because I recognize that everyone's situation has changed and your schedule may not match up with my schedule all that well. And if that's the only time available to you is at some unusual hour, if you prep it with me ahead of time, we can work something out.
Okay, so what time are you available tomorrow? Because I can
so
understand what's going on, but it's really hard for me to learn digitally because I'm a
take a look. So
person.
all right. I'm going to save myself some hassle here. So if you go into Canvas and you go into the syllabus, and
so yours didn't change.
Nope, I kept I went ahead. I looked at the survey that I sent out over spring break to see what people were available for, and I didn't see a whole lot of times that didn't jibe. So my official office hours haven't really changed. So, you can see here's my official office hours. Mm-hmm. And you can see I have office hours between my 2 morning classes, after my noon class. And those are times where I make sure that I don't go wandering off. I make sure that I'm, my computer is near me. So if I'm getting emails, I can respond to them. Other times, if it's not gray, I'm usually available. So, if it's 4 o'clock on a Tuesday and you need to get some help with homeworks, send me an email saying, "Hey, can we meet at 4 o'clock on Tuesday?" And I'm usually able to do so. I just can't guarantee that I'll do it during these hours. Whereas here, you should expect that if you ask for a meeting during this block of time, I'm going to meet with you because that's what that time is for.
Okay.
Yeah. I will virtually never say no during these. I might say no during those and try to reschedule. But by by all means, I get that this class is hard and that you're working under, compromised situations right now. So ask for help. That's literally my job.
Okay, because I definitely got some questions.
Okay. All right, guys. Any other questions?
No, I'll see you in about 4 minutes.
Okay.
Nope. See you.
All right, folks.
Friday.
See you Friday. Do your homework. Study hard.
Okay.
Jesus, take the
All
wheel.
right, bye.
Jesus helps those who help himself. Do your homework.